Hello. We're going to try to compare linear momentum and angular momentum. So first we'll consider a point mass right here, this M here, and it's sitting in the merry-go-round and it's going around in omega right now. So we don't care too much about merry-go-round. We just care about this point mass right now. It's a constant angular velocity omega, and the radius is r, and this is the exo. So its linear velocity will be constant v, and that v will be r times omega. So this point mass is m. Its radius is much smaller than this r here. So we can consider that as a point mass. Okay, so if we want to calculate the angular momentum for this point mass m, the L is equal to I times omega. So by definition. So that's equal to I, it's equal to mr squared. So mr squared by definition. And this omega, it's equal to v divided by r. So we're going to put that in, and then you just cancel the term r, cancel the r, and then it become mrv. So that's for point mass on this formula. Sometimes it's quite useful to remember this point mass. When you have this r radius from the exo, it will be mrv. So now let's consider angular momentum conservation problem. Okay, so based on the previous formula, we're going to apply that into this problem of conservation of angular momentum. So we have a disk initially at rest, and we have a point mass that's shooting at it, and after the shot, it got stuck. So we want to find the omega of this system, which is m, the point mass, plus the disk after the collision, after this one collides with this one. And we assume there's no frictional torque at the exo. So the way we solve it is, since the external torque, the net external torque is equal to 0 for this system, these two together. So then we can apply conservation of angular momentum. And to do that, we have angular momentum in the beginning, which is only possessed by this point mass. And there's m, v, and r. So the moment it touches, it has the mrv, which is the initial momentum, right before the collision. This is before collision. Afterwards, when they stay together, this I times the omega, and the omega is together, they're going to be rotating with this omega. So the point mass and the disk. And this combined I is from the disk, the solid disk, and also the point mass on the disk. So the solid disk is 1/2 mr squared. And this point mass on the disk is going to be mr squared. So together is 3/2 mr squared. So we can plug this one into the I here, and then we equate this two. So that's what we have, mrv, which is Li, it's equal to I, which is 3/2 mr squared right there, times omega. And that's what we're trying to find, the after collision. So now we cancel the m, we cancel 1r. So now we're left with v is equal to 3/2 r times omega. Since we're looking for omega, we rearrange this term to the left-hand side here. So we have 2/3 v divided by r. So this way we can find what is the omega, okay, after the collision, right? So that's an explication of using the previous formula that we just learned, right? So see you until next time. Bye-bye.